All right, so this video is going to focus on acid-base reactions, but we're going to start with just a little bit of acid nomenclature, as we've encountered this a couple of times so far. But I know when we first talked about acids in your first year chemistry class, we didn't get into as many of them as we will in this class, and we also didn't really talk a whole lot about the rules that go into naming acids. So you can find acids both in solid form and in aqueous form. The acids we're going to be dealing with in this class are going to be in aqueous form. So to name those particular acids, we have to look at the anion that is found with them. If the anion does not contain oxygen, if it is ending normally with IDE, then those particular acids get named with hydro at the beginning and then ic acid at the end, and the middle is the root of their name. If the anions are oxyacids, or if the acids come from oxyacid ions, ones that contain oxygen, they'll end in ate or ite, and the ending determines how their name is going to be formed. They will never start with hydro, but if the anion ends in ate, they will go to ic acids, and if the anion ends in ite, they'll go to us acids. When we're writing our formulas between ions that make up acids, we have to balance out our charges, knowing that hydrogen is always going to be acting as our cation, and then whatever the anion is either going to directly balance with it, or we'll have to cross charges to get the same number of charge positively and negatively to make the overall molecule neutral. So here are some examples. We're going to start with formulas and work our way to names. Then we're going to take names and turn them into formulas. Here we have HCl. So Cl is coming from chloride, so that would become hydrochloric acid. HCN is not straight from the periodic table. Most of your ides are from the periodic table, but CN is cyanide, so it's going to follow the same naming system as HCl did. Ides start with hydro and end with ic, hydrocyanic acid. The remaining two formulas have oxygen, so that tells us right there they will not start with hydro, but they will either end in ic acid or ate acid. SO4 is sulfate, so that's going to become sulfuric acid. Now that might sound a little weird. That's not really a root, but sulfic acid doesn't sound so great, and so that's why they went with a little bit longer of a name for that particular one. We'll also see that with phosphorus. I will not take off if you use sulfic acid on something. SO3 is coming from sulfite. So again, as opposed to sulfus acid, that's going to be sulfurous acid. And then we have some formulas to take a look at with hydroselenic. Again, hydro means that it's coming from the periodic table, so that's selenium on the periodic table, Se-2 selenide. And so to balance out that particular formula, we would need to cross charges and have two hydrogens, H2Se. Now, the polyatomics that end in ate or ite sometimes do have other parts to their name, and we see that with perchloric because that's perchlorate. And so the ics, again, are going to be your polyatomics ending with ate. So we have ClO4 minus, and because those have the same charge, just opposite in sign, we just get to sandwich those two ions together. Phosphorus, us, tells us that's coming from phosphite, and that's PO3 minus 3. So when I put those particular ions together, I get H3PO3 as my formula. Chromic is coming from an 8 because there's no hydro. We know it's a polyatomic. Chromate is CrO4 minus 2. So we're going to need to balance out charges, and our new formula would be H2CrO4. Nitrous, again, is coming from an ite polyatomic, which would be nitrite. That happens to be NO2 minus. Those two balance out charge-wise, so we get HNO2 for our formula. And then finally with hydrobromic acid, hydro tells us that we're coming from an ide ion. Bromide is from your periodic table. It has a charge of -1, and so they two would cancel each other out, and you would get HBr for its formula. So you do need to be familiar with how to take names of acids and turn them into formulas, and how to take formulas of acids and turn them into names. So hopefully that's enough to help you be able to do that. And we're not trying to make you memorize every possible acid name or formula, because as opposed to Chem 1, there are way the heck more acids than you encountered there. Speaking of acids, we're just going to briefly go over some definitions of acids and bases. I know we talked about this a little bit previously. Arrhenius determined that acids are going to be substances that are able to make hydrogen ions in solution, while Bronsted-Lowry said that they can donate protons. And for the most part, our acids donate hydrogen as their proton, so that definition wasn't really much broader than Arrhenius's definition. Acids can act as strong acids or weak acids. If they're strong acids, as we've seen before, they completely ionize. You already know that list. We've talked about them. And they go completely from being an aqueous solution to be ionized. While weak acids only partially ionize, and so they have that double arrow happening because sometimes they separate, but more often than not, they stay intact. And it just really depends on their relative strength as to what percentage of their molecules are able to dissociate into ions. We can also have acidic oxides, and those are oxides that contain the nonmetals carbon, nitrogen, and sulfur. In the presence of water, they can form acids, and so that's one of the big issues with some of the greenhouse gases, is that as those concentrations increase, they can combine with precipitation to produce strong acids or weak acids that then are going to change the pH of our soil and our water. Bases are Arrhenius defined as a substance that is able to make hydroxide ions in solution. Bronsted-Lowry actually expanded that definition by saying that they can anything that is a base that can accept a proton. While hydroxides can accept protons, but also can electronegative atoms like nitrogen, and that's why we've talked a little bit about how weak bases are going to have like that NH group. So your strong bases are anything that is a hydroxide compound that is able to be dissolved in water. So your group 1 hydroxides, calcium, barium, and strontium hydroxide are all examples of strong bases, while your weak bases are going to have that amino group, or they could have another hydrogen replaced or the other 2 hydrogens replaced on it with hydrocarbons and ammonia. And in both cases, those weak bases only go through a slight dissociation as opposed to sodium hydroxide or any other strong base, which will completely dissociate into its respective ions. We talked about acidic oxides earlier. Basic oxides also exist. They're the ones that contain alkali or alkaline earth metals, and in the presence of water, they will make bases. So calcium oxide, when it combines with water, will produce calcium hydroxide. Generally speaking, with acid-base equations, if you have anything involving any type of acid, doesn't matter if it's strong or weak, and you have one of your strong bases present, you're going to make water and a salt. It's going to follow the classic double replacement reaction, and that's the neutralization reaction you were probably familiar with from your first chemistry class. When you have a weak base present, you don't have that hydroxide component, so you actually don't end up making water. You will have the acid join with the base, and together they're going to make a salt. So the hydrogen from the acid joins on to any hydrogens associated with the NH group, and then the anion from the acid makes up the other part of your salt. And so the example I gave you there is of a strong acid, strong base, but again, it doesn't matter the acid. It's the base that's going to determine whether water gets made or just a salt gets made. So in this particular one, I will point out that NaOH is listed as a solid. And because it's a solid, you can find NaOH in my back prep room that I would have to add to water to get it to dissociate. So because it's a solid, it's a non-electrolyte, it does not separate. Your acids, however, are capable of separating if they're a strong acid, which HCl is. Water is in liquid form, so it's a non-electrolyte. And sodium and chlorine are making up an aqueous compound that is ionic, and therefore they too can separate. When I look at this particular equation, we saw with the precipitations, there were usually 2 ions that you could treat as common ions. That's not necessarily going to be the case with acids and bases. You really have to pay attention to their form and whether they are a strong or weak acid or base. In this particular example, the only component on the reactant side that was not transformed is the chloride. And so those are going to cancel out, And the net ionic is going to show the original base and the hydrogen ions from the acid combining to make water as well as sodium ions. So we're going to do some examples with this. We're going to start with H3PO4 and KOH, and we're going to determine what those products are, and then whether they can dissociate or not in the complete ionic, and then work our way to the net ionic. So if we are treating this like a double replacement reaction, potassium is going to go hang out with phosphate, and the hydrogens are going to hang out with hydroxide. So we want to write formulas between K and PO4 and H and OH. We have a strong base, so we know water is going to get made. And then if we write a formula between potassium and phosphate, phosphate's -3, potassium's +1, so we would have K3PO4. Why did I put AQ after K3PO4? Well, we have aqueous solutions to begin with, and we've made water, so we know water is present in this mixture, and we have an alkali metal. We also know all alkali metals are soluble, so that is why there's the AQ after K3PO4. I need to make sure my equation is balanced. I don't start with hydrogen because there's two sources of hydrogen on the reactant side, so I'm going to move on to phosphate, which is balanced, one on each side. Potassium, however, is not. I have one on the left and I have 3 on the right. And at this point, I have no choice but to deal with the hydrogens or the oxygens that remained. Keep in mind that phosphate has already been balanced, so I'm going to go ahead and take a look at O. I have 3 O's in KOH, and I have 1 O in H2O. So by putting a 3 in front of H2O, I now have all my oxygens balanced. I have 3 in the KOH and 4 in the PO4 to give me 7. I have 3 in the 3 H2Os and 4 in the K3PO4, also to give me 7. But for that to work out, the hydrogens need to be balanced. And so I look at my left side of my equation and I see I have 3 H's in H3PO4 and 3 in the 3 KOHs for a total of 6 H's as reactants, and 3 times 2 in the 3 H2Os gives me 6 hydrogens as products. So my equation is balanced. Now I need to decide of these 4 substances which are strong electrolytes, which can dissociate. H3PO4 is not one of your 6 strong acids. That's the acid that's found in soda. That's not something you want to that you would want to drink if it was a strong acid. So it's going to stay intact. But potassium hydroxide is an ionic compound with an alkali metal, and it's aqueous. So we know that particular compound will dissociate into K plus and OH minus ions. And because there's 3 of them, we need to have 3 of each ion present. Water is a liquid. It's a molecular substance. It cannot dissociate. But the K3PO4, again, we've already talked about how alkali metals are always soluble, so that can dissociate into 3 K pluses and a PO4 3 minus. If I look at my spectator ions, I see that I have potassium ions on both sides of the equation, but that's the only substance that is the same on both sides of the equation. So everything else would be included in my net ionic. Again, you can write the forms of the substances again if you wish, but that is not required. In this next example, we have an acid-base combination, but this time we're dealing with a weak base, so we know water's not going to get made. I know it's a weak base because I've got that NH making up the second compound on the reactant side. So as I said before, when you have a weak base present, the hydrogen from the acid is going to be lost and the nitrogen group is going to accept it. And then the anion, in this case the NO3, will become the second half of your salt. So C6H5NH3 plus is going to act as my cation, and NO3 minus is going to act as my anion. I know I have water present because those two are in aqueous solutions. And although I don't know diddly squat about C6H5NH3's properties and solubility, I know that all nitrates are soluble. So that's why I can put the AQ after that particular compound. When I look at my complete ionic, I see that I have a strong acid at the beginning that's in aqueous form. So I know that I can separate that compound into its respective ions. But I know weak bases are weak electrolytes and they do not dissociate. So C6H5NH2 is going to remain as a molecule. We talked about how nitrates are always soluble, and so because they're always soluble, they're going to be a strong electrolyte. And so that salt that formed on the product side will separate into its respective ions. If we look at both sides of the equation, we see that there are nitrates present on both sides. So those are going to be canceled out, and we'll be left with hydrogen ions and our weak base forming the cation of that salt. In this particular one, I didn't give you formulas, I gave you words, so we're going to have to translate this one. We have aluminum hydroxide pellets reacting with aqueous sulfuric acid. So aluminum hydroxide is our base. Hydroxide means it's a strong base. Aluminum is in group 13, it's +3. Hydroxide's -1. So when I write that particular formula, I would need 3 of the OHs to balance it out. And because it's in pellet form, that means it's a solid. We're then going to combine it with sulfuric acid. Sulfate is going to make up sulfuric, so that's SO4 - 2, so we need 2 hydrogens to balance it out. And we were told it's in aqueous form, so we can write it as H2SO4. Aluminum and hydrogen are going to switch places. We know when we have that strong base present and with an acid, we're going to make water. And then we're going to have aluminum and sulfate come together to make a compound. Aluminum's +3, sulfate's -2, and we have water present. We know that sulfates are soluble unless they're paired with calcium, barium, strontium, lead, silver, or mercury. So we're good on that front. That is going to be in aqueous form as well. To balance this, we need to get our aluminums in balance. We need a 2 in front of AlOH3. Again, I'm going to hold off on oxygen and hydrogen. I'm going to move over to sulfate. I see that I have 1 sulfate on the left and 3 on the right. So I'm going to put a 3 in front of H2SO4. My sulfates are balanced now, so the oxygens I need to balance are the ones in the AlOH3. I have 6 oxygens and 2 AlOH3 molecules. I only have 1 oxygen in water, so I need a 6 in front of the H2O. That gives me 12 hydrogens as products. And if I look at my reactant side, I have 6 in the 2 AlOH3s and 6 in the 3 H2SO4s, which would also give me 12. When I write the complete ionic this time, remember I only get to dissociate my aqueous strong acids and my aqueous ionic compounds. So the aluminum hydroxides do not get to dissociate. They're in solid form. They're a non-electrolyte. Sulfuric acid is one of my 6 strong acids, so it can separate. And again, I know I've said previously you would only lose 1 hydrogen at a time, and that would be the case if you just had water present. But because we have the aluminum hydroxide to react with H2SO4, it is able to pull all those hydrogens off of it. Water, as a non-electrolyte, is not going to dissociate, but our aluminum sulfate compound is an ionic compound, and it's in aqueous form, so it is soluble, so it will separate into 2 aluminum ions and 3 sulfate ions. If I look at both sides of my equation, I see that there are sulfate ions on both sides that are spectators, so it can be canceled out. And my net ionic equation is going to show what is left. Now, why did I reduce the coefficients? I have 2, 6, 6, and 2 remaining in my complete ionic equation. Well, those can all be simplified by a factor of 2, to 1 to 3 to 3 to 1. Here I have ammonia with phosphoric acid that is combining to make ammonium phosphate. If I ask you to make a salt with a weak base, and it is not straightforward what its formula would be, if I gave it to you in words, I would definitely provide a little more assistance with it. Please know that. But ammonia is one I expect you to be familiar with. Ammonia is NH3, and you were told it's aqueous, so I went ahead and put AQ after it. Phosphoric acid, I've said before, the acids that you're going to be dealing with in chemistry are going to be aqueous. Phosphoric is coming from phosphate, which is PO4 - 3. So that's going to give us H3PO4. And then we're putting those together to make ammonium phosphate. Ammonium's NH4 + 1, phosphate's PO4 - 3. And we were told it's aqueous, so we need 3 ammoniums to balance out phosphate's charge. If I'm going to balance this equation, it looks like I have 3 nitrogens on the product side, but only 1 on the reactant side. And if I hold off on hydrogen, since I've got 2 sources of hydrogen on the reactant side, if I take a look at my phosphates, they're good to go. So now if I look at my hydrogens, I have 9 hydrogens in the 3 NH3 molecules. I have 3 in the 1 H3PO4 molecule, which gives me 12. And on the product side, I have 3 times 4, which also gives me 12 hydrogens. So this equation is balanced. When I'm looking at my complete ionic, aqueous is always something I want to look for to determine if it can dissociate. But once I've determined, in this case, everything is aqueous, I need to look at what's making up those particular substances to determine if they are strong electrolytes or weak electrolytes. NH3 is a weak base. That does not dissociate. Phosphoric acid is not one of my 6 strong acids. It too does not dissociate. So you might be going, Barker, why the heck are we having to do any more with this? Well, if you look at your product, phosphates for the most part are insoluble, but ammonium and your alkali metals will dissociate in the presence of water. They are always soluble. And so the product will separate into ammonium ions as well as phosphate. There are no spectator ions in this particular example, so the net ionic would be the exact same equation as your complete ionic. That definitely can happen. But you don't want to just assume because the reactants couldn't dissociate that your products don't as well. So I think we have 2 more to do. We're going to take lithium oxide and we're going to combine it with water. Lithium oxide, lithium's +1, oxygen's -2, so that's Li2O. Water's good old H2O. And if you remember, I told you that basic oxides, metal oxides, combine with water to make base. So a base is going to have hydroxide with it. So we're going to take that lithium cation and combine it with hydroxide, OH -1, to make lithium hydroxide. And because we have water present and an alkali metal is making up our base, we know that this is a soluble base. To balance this particular equation, we need 2 lithiums on the product side, and that takes care of the oxygens and hydrogens, getting those in balance as well. We know we can't split apart solids. We know we can't split apart liquids. They cannot dissociate in the presence of water. But we can dissociate aqueous substances if they are a strong acid or if they are an ionic compound. And that is indeed the case, the ionic compound component in lithium hydroxide. There is, however, nothing that is acting as a spectator ion, so our complete ionic and our net ionic would be the same. Our final example is with dinitrogen pentoxide. It's a gaseous form and it's combining with water. So we're going to take N2O5 and we're going to add water to it. And when these come together, remember we talked about acidic oxides, that they can combine nonmetals with oxygen with water to make acids. So we have 2 H's, we have 2 N's, and we have 6 O's. And so if we think about the acids and the polyatomics that we're familiar with, you might be thinking about nitrate because you have 1 N for every 3 O's, and that's the ratio we have of N to O on the reactant side. Now, to balance this particular equation, we would need 2 nitrogens, and that takes care of the hydrogens and oxygens as well. Why did I say that that acid was aqueous? Besides that, I've already said that your acids are going to be aqueous. You've got water present, and we know that acids are always going to be soluble in water. A complete ionic cannot separate the non-electrolytes on the left side of the equation, the N2O5 and the H2O, but it can separate our strong acid in aqueous form into the hydrogen ions and the nitrate ions. Again, with your net ionic, nothing else is going to change since there are no spectator ions in this particular example.